Today's topic is about the alternative medical and scientific approaches. It means that we have already discussed about the heart diseases and also the organ transplantations, and it's especially about the from human to human, donor to the recipient transplantation. But to prevent this kind of event, the alternative approach we will discuss these 2 weeks. Firstly, about the medical approach, scientific approaches, and then the next week we will see at the engineering approach. Okay? はい、じゃあ、let's start. はい、today also provide much information. And firstly, about mainly about the heart disease. How to treat the heart disease? What is the heart disease, and how to make some medical operations to deal with this heart disease. And the second part is latest medical technology to deal with for the severe injured patient. First one is Batista operation for the heart, and the second is the hypoxemia therapy for the brain disease, severe brain disease, and then and finally about the regeneration medicine, regenerative medicine, and tissue engineering. Okay. Just start with the first one. The heart disease. Heart is the ischemic heart disease, IHD. That is because of the heart vessel become narrowed or the closed. So therefore the blood cannot be provided to the heart muscles, and then the heart muscle become weak or the dead. So therefore the heart attack or severe heart injury will be made. To deal with this coronary angioplasty will be made. Some kind of the medical operations will become made to make the wider of inside of the vessel, or the bypass operation will be made. The first one, some video I will show the heart attack. Overview. はい。ちょっとこれ見てみましょう。
The heart is fed by its own circulation, known as the major coronary arteries. These arteries include the left anterior descending artery, the left circumflex coronary artery, and the right coronary artery. The bloodstream contains red blood cells, which deliver oxygen to the heart muscle, known as the myocardium. It also contains fats or lipids, known as low-density lipoproteins, or LDL cholesterol. Atherosclerosis begins when LDL cholesterol accumulates in the arterial wall, forming a plaque. Over time, the plaque becomes larger. Some plaques never obstruct the coronary blood flow. The patient with asymptomatic coronary disease has no chest pain and no myocardial ischemia. A plaque can enlarge to the point that the blood flow is compromised. The patient may have chest pain, but only with exertion. This syndrome is known as stable angina and is not a clinical emergency. Such a patient is still at risk for an acute life-threatening event because a plaque can suddenly rupture, causing clotting of the artery, known as coronary thrombosis. When a thrombotic occlusion is subtotal, an acute coronary syndrome develops, and there are 2 types. The first type is known as a non-ST segment elevation myocardial infarction, and the second type is known as unstable angina. With these syndromes, the patient experiences chest pain at rest, and the electrocardiogram shows ST segment depression. In contrast, when the thrombus completely occludes the vessel, the myocardium is injured, and the syndrome of ST segment elevation myocardial infarction develops. In summary, Patients with coronary artery disease may be asymptomatic. They can have stable angina, or they can suffer an acute atherothrombotic event. Plaque rupture with coronary thrombosis is the most common cause of acute, life-threatening coronary artery disease. Emergency therapy by thrombolysis, angioplasty, or thrombectomy restores blood flow by targeting the thrombus, either dissolving it, displacing it, or removing it as quickly as possible. Rapid restoration of blood flow relieves symptoms and minimizes myocardial damage.
ということで、inside vessel, firstly, the plaque ですね。Mainly about the protein or some other material will become here, and if it is injured, the thrombus, the blood cell will become gathered and make this inside of this vessel narrow and stopped, closed. So therefore, after that part, the oxygen will not be provided. So therefore, the heart muscles will become damaged, become weak, and sometimes dead. So therefore, firstly, some drug will be provided, and then this should be melted out. So this is the first approach to deal with this. And then secondly, the balloon method is there. This is a catheter, and then this tube is a rubber tube will be here, and then it is become large by using some liquid will be filled inside of this balloon, and then it makes the wider. And then if it is wide enough, it will be released. But in this case, sometimes it becomes again to become narrow, so therefore it's not good enough treatment. This is only the one's tentative treatment for the immediate operations. It's okay. This is balloon method is firstly widely used, and to keep this widened condition, this insertion material, this kind of metal mesh will be inserted, and then keep this part opened. To keep this part opened, this kind of metal mesh will become inserted outside of this balloon, and the balloon, once it is extended, this stent, it is called a stent. Stent will also be extended, and then kept inside the aorta, heart vessels. It is like this. 中見ましょうか。これか。このクローズパートでこのステントをinside of this30mm long って書いてあるんですけど、このカテテルを入れて、このバルーンを膨らませて extended this balloon, and then the stent will be put. Stent このメッシュが見えますね。You can see this mesh here. で、keeping this part wide, opened っていう です。はい、っていうような感じです。というのはこれね、ステント。で、but this part is plaque or the thrombus is remaining, but after some period it is broken and sometimes the blood will become released from here. So therefore it's not good enough in some cases. So therefore this plaque or thrombus should be cutted and cut it. So therefore this kind of cutter is inserted here. This part, this is a cutter, and this is the insertion material. This is the storing part. So therefore the cutter will become rotated and cutting this part and push it into this side. And in this part, this is released. So this kind of method will also be made.
DCA, directional coronary atherectomy, like PTCA, is a minimally invasive procedure to remove the blockage from the coronary arteries and allow more blood to flow to the heart muscle and ease the pain caused by blockages. The procedure begins with the doctor injecting some local anesthesia into the groin area and putting a needle into the femoral artery, the blood vessel that runs down the leg. Once the needle is inserted, a guide wire is placed through the needle into the blood vessel. Following this step, the guide wire is left in the blood vessel and the needle is removed.
この、ガイドっていうのは大体この inside of this, it is this inside of this because this vessel is become larger diameter, so therefore the inserted from this in many cases. It is also close to the skin surface, so therefore it is easy to insert from here.
An introducer is then placed over the guide wire, after which the wire is removed. A 35,000th inch guide wire is put in its place. Next, a diagnostic catheter, which is a long, narrow tube, is advanced through the introducer over the 0.035 inch guide wire into the blood vessel. This catheter is then guided to the aorta, and the guide wire is removed.
Guide wire のところにチューブを入れて、そのコロナリーアーテリーで
Once the catheter is placed in the opening or ostium of one of the coronary arteries, the doctor injects dye and takes an X-ray.
X-ray で this part will
If a
become
treatable blockage is noted, the first catheter is exchanged out over a 0.035 inch guide wire for a guiding catheter, after which the wire is removed. Once the guiding catheter is in place, a 14,000th inch guide wire is advanced across the blockage. Then, a catheter designed for lesion cutting is advanced across the blockage site. A low-pressure balloon, which is attached to the catheter adjacent to the cutter, is inflated such that the lesion material is exposed to the cutter. A drive unit located at the proximal end of the catheter is turned on, spinning the cutter. A lever on the drive unit is advanced by the physician, which in turn advances the cutter, cutting away pieces of the blockage. These lesion pieces are stored in a section of the catheter called a nose cone and removed after the intervention is complete. Together with rotation of the catheter, the balloon can be deflated and reinflated to cut the blockage in any direction, allowing for uniform debulking. A device called a stent may be placed. This is a latticed metal scaffold that is placed within the coronary artery to keep the vessel open. After the intervention is completed, the doctor injects contrast media and takes an X-ray to check for any change in the arteries. Following this, the catheter is removed and the procedure is completed.
この this method は after cutting this part and then the state will be placed on here to keep this opening condition. And presently, more other recent material equipment will be developed like this. So therefore, some of them I will show in here.スクリューインカッターみたいですね。やっぱりスロンプスがこうスクリュードリルでこのスロンプスアキュムレイティング。っていうようなこうニュートゥールとかできてるんですね。どうかちょっと他にもこれをちょっとあげますか。はい。メガバックってやつ。
Of the 1 million heart attacks that occur in the U.S. every year, 375,000 are ST elevation myocardial infarctions, involving large coronary thrombi that are eligible for thrombectomy. In addition, each year over 200,000 patients with peripheral arterial disease are in need of clot removal. Rapid and complete removal of arterial clot from either coronary or peripheral arteries can potentially salvage tissue, improve clinical outcomes, and reduce mortality. Unfortunately, existing thrombectomy devices suffer from major limitations. Simple aspiration catheters often leave 30 to 50% of the clot behind. Multiple catheter exchanges are needed when large clot is present. In addition, mechanical thrombectomy devices are associated with a high risk of adverse events, particularly distal embolization. Fragmentation of the clot during thrombectomy frequently occurs, sending hundreds or thousands of emboli distally, which leads to reduced blood flow, tissue death, and significant morbidity and mortality. The Megavac vacuum extraction thrombectomy system solves limitations of existing technologies, setting a new standard in clot removal. The Megavac is actually 4 devices in one. It occludes the artery completely. It protects against embolization. It acts as an anchoring device, and it rapidly, completely, and efficiently removes arterial thrombus. Let's watch how Megavac vacuum extraction thrombectomy works. The catheter is first positioned just proximal to the clot. The funnel mouth at the tip of the catheter is then deployed, occluding blood flow with its silicone elastomer on the distal aspect of the funnel. This results in the mouth of the funnel tip being maximally expanded in a radial fashion by the patient's own blood pressure, creating a seal against the arterial wall and arresting blood flow. Cessation of blood flow prevents clot fragments from traveling downstream, greatly reducing the potential for distal embolization. The patient's blood pressure, along with the radial force of the funnel tip, combine to press the device against the arterial wall, anchoring the catheter firmly and safely. The outward expansion of the Megavac anchors and centers the device,
and can be used as an anchor for other devices in crossing tight lesions or tortuous vessels. Once the megavac arrests blood flow, the thrombo wire is inserted through the catheter, advanced through the clot, and deployed distal to the clot. While applying suction with a medevac, the thrombo wire is retracted to simultaneously pull the clot into the funnel mouth and through the catheter. After complete clot removal, suction is discontinued and the catheter tip is undeployed, restoring distal blood flow. Rapid removal of occlusive thrombus with vacuum extraction can accelerate door-to-balloon time and improve outcomes. In summary, there is currently a large unmet need for rapid and efficient thrombus removal in cases of coronary and peripheral arterial thrombosis. The medevac system provides a 4-feature solution in one device: occlusion, protection, anchoring, and removal. Medevac is easier to use, with the potential to be safer and more effective than current devices, which translates into improved blood flow, less tissue death, and more patients' lives saved.
っていうやつです。このバキュームっていうかサクションね、サクションメソッド、various instrument will become developing now also. というわけでした。The second part, not only the inside of this cardiac vessel. There is another method. Another method is provide some new bypass to supply the blood for the following vascular vessels. Following heart muscles. Okay. So the new approach way to provide the heart to provide the blood will be made. So the bypass will become put it into from the another part. So therefore, this is a living heart, and using the heart lung machine, the surgical treatment, surgical operations will be made. So therefore, by using this stabilizer, pushing these forks on this heart and make this part stable. And then the medical doctors will make some surgical operations. ね、っていうわけで、ちょっとこれも見ますかなんか。例えばね、これか、スタビライザー。
Coronary artery bypass graft is a commonly performed procedure to reroute the flow of blood around a blocked coronary artery. During most bypass surgeries, the heart is stopped and a heart-lung machine takes over the work of the heart and lungs. Although most traditional bypass surgeries are performed successfully, some patients experience temporary memory loss or other side effects that may be associated with the heart-lung machine. Off-pump coronary artery bypass surgery, or OPCAB for short, allows the surgeon to perform a bypass without stopping the heart. In one form of OPCAB, the chest is open and the surgeon uses a stabilization device to restrict the heart's motion. A small elastic tape may be placed around the blocked artery to stop the flow of blood. A vessel taken from another part of the body is attached from the aorta to a point beyond the blockage. The clamps are loosened and blood flow resumes through the repaired artery. Some patients may be candidates for a less invasive version of the OPCAB, called MIDCAB, or minimally invasive coronary artery bypass. A small hole is made in the patient's left side. The heart is stabilized and the patient's mammary artery is used to detour blood around the blocked coronary artery.
ということで、だから open this chest and this bones will become kept open. So therefore, some material is given to keep this part open. And then on this heart, this fork-like stabilizer is put it on, and then putting this and this former part and after part is pulled, and then this part, new bypass is attached here. So therefore, the this tube is necessary. Where this tube is provided is looks like this. So this is, for example, about which vein, which blood vessel will be provided to here. The first one is the great saphenous. This is the inside of this. Some vein is cut from here, and then this is used from this part to this part. New bypass is made. The second one is here for the lung providing the artery. This artery is cut and put it on here, on this part. Part is the second one. And third one is the stomach part. Some stomach is also has some veins, the arteries. So therefore, the one artery is cut from here and put it on the heart. This is the third one. And then the fourth one is inside of this part. So it is cut out and provided to like here. This is 4 cases. From other vessel will be used to provide the heart, provide the blood to the heart. Okay? This is the bypass operation. This is the first part about the heart operations. And then the next one is recent approaches. This is a Batista operation to cut the heart muscle directly. Because some patient has some diseases like the bigger of these muscles, of these heart muscles, because the heart is a pump, as you know, and this is some vessels. Artery is here, and the heart is working a pump. If this blood pressure become, so the blood pressure is very important. Okay? Pressure. If the blood pressure is become higher, the heart should work to provide the blood to the entire body. So if the workload become large, the heart should become more stronger and stronger. So it means the muscle part will become stronger, and the muscle part become thicker and thicker, and then the bit become larger, heart become larger to provide enough blood. Amount of blood should be provided to the entire body. So therefore, some athlete makes the heart larger, and also some elderly people become, because of the high blood pressure disease. So therefore, the heart become larger. It may not good for, and then this heart muscle become thicker. Its flexibility become lost, and then the total heart function become decreased. So therefore, some method is necessary. In past, it should be no good treatment for this kind of disease. So therefore, the heart replacement is necessary. But one Brazilian surgeon, Batista, started cutting this part. This thick part will be released, and then after this surgery, some good recovery condition will be observed. So therefore, it is widely used in the worldwide. いいですか。はい。ですね。これオペレーションです。is here. はい。The second part is hypothermia for brain injured. If the brain is severely damaged, the treatment is very, very difficult because how to provide the water, how to provide the oxygen is very, very sensitive conditions. To how many, too many oxygen will be provided. The oxygen is also necessary, and the oxygen should be used in the brain to keep the brain functions. But water providing and the temperature providing, oxygen providing is necessary, but the treatment is very, very sensitive. But so therefore the one method is for several days, keeping the activity of the entire body will become reduced, and then the natural recovery will be expected. So therefore, not only brain but also the total body, entire body lower temperature keeping is the one method. By using the water cooler mat or water cooler blanket will be given to the patient, and then after several days the temperature, body temperature will go back to the normal condition, and then the recovery will be expected. So this kind of water bracket will be given to the patient, and then the monitoring the entire body conditions, and then the taking care of some energy will be provided, and then the temperature will become kept lower, and then the observing the patient conditions. ちょっとなんか見てますか？セラピーハイペルザートリートメントハートアタック。これか。はい。
When the heart decides to not function correctly and we need to do CPR in order to get it back beating normally, we have decreased blood flow to the brain. And that's when people become anoxic, they don't have enough blood flow to the brain, and it can adversely affect their brain function forever. So by using therapeutic hypothermia, we are slowing all that process down, slowing down the metabolism for a full 24 hours, and then rewarming slowly to allow the brain to restart and hopefully come back to its normal functioning state. We try to get them cooled rapidly within 4 to 6 hours after they've had return of spontaneous circulation. That's the first phase, which is the induction, which goes very quickly. And then the maintenance phase is the second phase, and that usually lasts 24 hours. We do keep somebody chilled at 33 degrees Celsius for 24 hours. Following that, we start a 16 to 20 hour rewarming phase. We rewarm slowly because that seems to help the brain slowly recover after it was without oxygen, which all was involved with the cardiac arrest. If we receive a patient from a different unit in the institution or from outside the institution, routinely they have already been started with a little bit of cooling down by having ice packs placed under their arms, up around their neck. We also give 2 liters of ice saline over a 30-minute time frame, either through a central line or through an IV line. We apply the pads, and there are 4 pads that are placed on every single patient. We have 2 pads that are placed on the upper torso. It goes from the spinal column in the back and wraps around the front. Then we also have 2 pads that are applied on the patient's thighs. If the individual has a rather large abdomen, we want to try to cover as much skin as possible to cool as rapidly as possible. So we do have a universal pad that we can use as well on somebody with a rather large abdomen. Those pads then are connected into the Arctic Sun machine. We do turn the Arctic Sun machine on, and we can set it for hypothermia. And right away, we will start having chilled water moving into the pads. And it's a constant fluctuation and moving. It should be around 33 degrees once the patient reaches its maintenance therapy to maintain them at 33 degrees for 24 hours. Once we have a patient back up to 37 degrees Celsius or 98.6 degrees Fahrenheit, the recovery phase then really starts for the individual. We have seen a variety of success stories through somebody waking up and responding to our request soon after we have them warmed. We have had individuals 2 weeks out. That, not that we were losing hope, but it was really a struggle because we weren't seeing a lot of interaction, and suddenly people will open up their eyes and they do respond to our requests. So it's very individualized.
というわけで、lower temperature operation will be made, and it shows a good recovery ratio. Okay. And the third part, final part, is regenerative medicine. Maybe you are very interested in about regenerative medicine. Because maybe you may understand about at the time of the medical materials. At the time of medical materials, you have learned about the diffusing functions for your own body, the others, something or other different from the natural material is not good. But to the regenerative medicine, mainly using your own cell will be used. So therefore, no necessary thinking about the diffusing functions of your body. So therefore, the regenerative medicine is very important and very expected to do in place of the organ transplantation or some other method. Firstly, only the cell will become transplanted, and then the tissue or the organs will be generated and then transplanted to the inside of your body. That is two approaches. One is only using the cell, and the other is after making the tissue or organs, and then after that it is transplanted in your body. ということで、regenerative medicine ね、なんか見ますか？Some introduction part. あ、これは長いな。
Talk to you today about hopefully converting fear into hope. When we go to the physician today, when we go to the doctor's office and we walk in, there are words that we just don't want to hear. There are words that we're truly afraid of. Diabetes, cancer, Parkinson's, Alzheimer's, heart failure, lung failure, things that we know are debilitating diseases for which there's relatively little that can be done. What I want to lay out for you today is a different way of thinking about how to treat debilitating disease, why it's important, why without it perhaps our healthcare system will melt down, if you think it already hasn't, and where we are clinically today and where we might go tomorrow and what some of the hurdles are. And we're going to do all of that in 18 minutes, I promise. I want to start with this slide because this slide sort of tells the story the way Science Magazine thinks of it. This was an issue from 2002 that they published with a lot of different articles on the bionic human. It was basically a regenerative medicine issue. Regenerative medicine is an extraordinarily simple concept that everybody can understand. It's simply accelerating the pace at which the body heals itself to a clinically relevant time scale. So we know how to do this in many of the ways that are up there. We know that if we have a damaged hip, you can put an artificial hip in. And this is the idea that Science magazine used on their front cover. This is the complete antithesis of regenerative medicine. This is not regenerative medicine. Regenerative medicine is what Business Week put up when they did a story about regenerative medicine not too long ago. The idea is that instead of figuring out how to ameliorate symptoms with devices and drugs and the like, and I'll come back to that theme a few times, instead of doing that, we will regenerate lost function of the body by regenerating the function of organs and damaged tissues, so that at the end of the treatment, you are the same as you were at the beginning of the treatment.
まあ、リジェネレーションですよね。リジェネレーション by yourself, using your own body, own cell, is one important idea. The history, this is the history. Firstly, the 1981, the Boston's group is made the skin tissue, the generations, and then the NSF has become the sponsor about the tissue engineering. And then the next, maybe the ear mouse is very famous. About you have watched, you may have watched about some pictures or videos about this ear mouse. I will show later. And then the next to some other part will become widely tried, and then the ES embryo stem cell, and other stem cell, germ cell is also used for the source of this tissue engineering. And then the blood vessel is also will be made, and then the other tissues is also tried. The tissue engineering, this is the cell culturing technology plus the material engineering, and then the medical engineering will be combined, and from the single cell, some tissues or some organs will be made. But to make the target tissue, target organ, how to cultivate the cell is one important issue. How to control to make this tissue, make this organ is a very complicated problem. Some physical stimuli and chemical stimuli, or some the material given, or some electric force applied is tried to make the target tissue or target organs. But not already solved this kind of problem completely. To make the tissue engineering, the one important is of course the source cell is necessary, and then after making the source cell, for example the ES cell, EG cell, the scaffold you have to remember about this word. Scaffold is some structure, three-dimensional structure to make the tissue or to make the organ, the target organ. And then the proliferation is cultivating the cell from the stem cell or some progenitor cell, putting onto this cell, this single cell will become cultivated and differentiated to make the muscle or fat or bone or some organ or tissues. And then the adjustment, some factors, growing factor is necessary. So therefore, some material will be provided, and this phenomena have not been solved enough. So I will show something video to provide to explain about the tissue engineering. Yes.
Hey everybody, I'm Katie correct this is eye to eye. You know, it sounds like a Frankenstein fantasy, but the science of growing organ tissue is on the verge of some pretty unbelievable breakthroughs. Wyatt Andrews caught up with one researcher for a tour of what you might call the laboratory of the future. Check it out.
These incubators are oven-like devices. They have the same conditions as a human body, 37 degrees centigrade, 5% CO2, 95% oxygen, so they have actually the same conditions as you have inside your body. And then it opens up like an oven, but instead of having shelves with baked goods, you actually have shelves with cells. And
that's warm.
That is warm. So this is actually body temperature. Right. That's the same temperature as inside your body. And then inside you see different kinds of plates, and these plates are all full of different kinds of cells.
What might be in there, or what is in there?
Actually, these are stem cells which have been derived from amniotic fluid. So this is a new type of stem cell.
Amniotic fluid, stem cells.
Correct. This is your typical tissue culture hood, and this is actually where we take the cells and start expanding them. And these cells grow exponentially. You grow the cells in a plate until they fill the plate, and then you split the plate into 6 other plates, and then we take those 6 plates, we split them again, and now we have 36 plates, we take those 36 plates, we split them again, and it's an exponential growth.
But you're describing a situation where once you start this process, you can grow as much tissue as you need?
In fact, that is true, especially if we're using the stem cell populations. If we're using cells from your own body, which we can also do, then there's more of a limit on how many cells we can use, but we can certainly make enough cells to create tissues and organs that we can implant back into you. Here you see a engineered blood vessel, and so you can actually see the vessel beating, and it's pulsating. And this is how we mature these engineered blood vessels. So this is actually an engineered blood vessel that's being ready, that is ready to be implanted.
Are you telling me that you are growing the blood vessel right there?
That's exactly right. That's actually an engineered blood vessel. So this is actually a blood vessel that has been grown using cells. And so the outside has the muscle cells, and the inside has the vascular cells. You can see they're different sizes, different widths, different depth in terms of the consistency of the tissue, because they're all custom made, right? They all have different applications, and we actually match the creation of the blood vessel to fit exactly the specific patient, if you will.
Okay.
But
まあいいや。ということで、stem cell is necessary. How to get the stem cell?
Okay.
One is the egg cell plus the other nucleus is inserted into the egg cell. This is one source. And the other source is a fertilized egg. Fertilized egg is, of course, the source of the human. So therefore, that is becomes the ethical problem. So therefore, basically, we should use only the egg cell plus from other nucleus is inserted into the egg cell. And then after some cleavage, the inner cell mass is here. From this, ES, embryonic stem cell, embryonic stem germ cell will be made. And then what is the ES cell, EG cell? That means the stem cell is the ability of the differentiation. It is one single source, but it can be divided in other many various kind of functionalized has some potential. So it means this cell has much potential to become working for the specific cell. For example, some muscle cell, some of them is the blood cell, or some of them is bone cell, and so on. So therefore, this single cell has some potential to become the various cells. for bones and heart muscles, blood vessels, or some the soft bones, or and the skin, or something. So only the source is the same, only the one single source, but it is differentiated to the various functionalities. So it means that this is very important. So how to get this stem cell is very important. What can stem cell do? Yes, I will show this.
Hey there, welcome to Life Nugget. Over the course of human history, medicine has come quite a long way. Centuries ago, we thought the body was composed of different liquids called humors. And if you were unlucky enough to get sick during this time, your blood would have been withdrawn in a process known as bloodletting. Gross. In modern times, we can give antibiotics, perform open heart surgery, and even operate on the brain. However, one of the newest advances in medicine is stem cell research. You may have heard of stem cells before, but there's a lot of mystery about what they actually do. Why is it such a promising new field? Well, to answer this, let's shrink down to the size of a cell. Normal cells in the body are specialized. We have neurons in the brain, red blood cells in our blood, and cells that make up your muscles and bones. All of these cells carry the same DNA, which is unique to you, unless you're an identical twin. But what makes the cells different is that some of them have certain genes turned either on or off. The genes are encoded in the DNA, which is all the same, but the gene expression is different. This means that the genes expressed in a red blood cell are different than the genes expressed in a lung cell. And that lung cell will always stay a lung cell. It will not change into a red blood cell one day. However, stem cells can. Stem cells are unspecialized cells that give rise to specialized cells in a process called differentiation. When a stem cell divides, the new cells can either remain as stem cells or become other cells with a specialized function, like muscle cells. There's a lot of cell talk, but we're going to keep going. There are two main types of stem cells, those found in adults and those found in embryos. Somatic or adult stem cells can be used to repair and maintain the tissues in which they are found. These can be found in the brain, skin, and bone marrow. In fact, during a bone marrow transplant, stem cells are injected into a patient whose bone marrow was damaged somehow. The unspecialized stem cells then create new bone marrow, allowing for the body to produce healthy blood cells again. Stem cells can also be used for organ and tissue regeneration. If the cells differentiate in just the right way, they can act as a renewable source of replacement cells. For example, stem cells beneath the skin can be used to make skin grafts for burn victims. And this could eliminate our reliance on organ donation and make the wait list for transplants a lot shorter. Stem cells also have the potential to replace damaged brain tissue, treating diseases like Alzheimer's and Parkinson's. Furthermore, embryonic stem cells could differentiate and form insulin-producing cells that can treat people with type 1 diabetes. And the list of treatments goes on and on and on. The main controversy with stem cells, however, involves those taken from embryos. It's important to note that these cells are not obtained from fertilized eggs in a woman's body. Instead, they are gathered from eggs in an in vitro fertilization clinic. These are the eggs that were not implanted in a mother's uterus and were willingly donated for research purposes. But this does beg the question of whether or not a life was destroyed in the process, which ultimately leads to the debate. The use of stem cells are seemingly endless. We've come a long way since our humble beginnings, and will hopefully continue to advance. So tell me, have you had any experience with stem cells or organ donation? Or maybe you know someone who has? I'd love to hear your or their story. And if not, let us know in the comment section below what you want us to talk about next. Make sure you come back every Monday and Thursday for a brand new video. And if you want...
If you are interested about the ethical problem about the stem cell, you should watch these videos later about the problem, the ethical problem about the stem cells. And if you have no time to watch this, maybe, so therefore I will go to the next part. The three-dimensional cultivation. So once the stem cell is generated and then cultivated, it is put on some the three-dimensional scaffold. Scaffold is to put these cells onto this. It makes some the structures of the cells. To do this. This kind of three-dimensional scaffold, there's a base material, like some ceramics or some gels or some fibers is given here. And then in some case, some physical stimuli is given, some stretching and shearing or some the hydraulic pressure is given, and then the target target cell will be made. さあ、ちょっとティッシュエンジェリングどっか。さあどれがいいのかな I don't remember which is a good. Yes, first one. これは last week I have shown this island promotion video. で、これクローン is made in some island. Some rich person's tissue is cultivated, and his cloning human is growing there. Harvest body parts from the clones って書いてあるんですけど、これなんかオルガンをカルティベイティ安全なトランスファーもちろんオルガンショーテージ and failures。Tissue engineering is important. This research group said saying. Patient のオンセルで3D dimensional, how to make the 3D-dimensional organ tissue is a very important issue. Firstly, challenge ですね。cultivated. And then the seed on the three-dimensional scaffold で cultivated. Extracellular material. なんかファイバーライク作戦。 more and more fine fiber structure is good to make the three-dimensional organs. で、なんかマイクロファイバー is good っていう。This group is using the electrospinning method to make the thin fiber, nanofiber structures っていうのが This research group's saying ですね。まあそういう話がこれにありました。いいや。ということで、presently the many various kind of tissues and organs is under development, under researched, under searching. And some of them is clinical applied presently, and some of them is not only clinically but the practical used for the bone or some other tissues. For example, this is the ear mouse. This 1995, the BBC's the documentary program showing this, and then the very astonished about this. The living mouse is generating this the ear-like organizations, and then this mouse ear. 見てみますか? Artificial human ear growing in mouse. とかちょっとこれ見ますか?
Years ago, transplant surgeon Jay McConkey and chemical engineer Robert Langer realized that to build an organ, cells also need a framework, a scaffold to guide their growth. The challenge was to engineer scaffold materials living tissue could grow on.
So this is a material that we call biorubber.
Biorubber, and you use the prefix bio because whatever is the material it will take to flesh or living cells.
That's right.
So why does the cell even care?
Because a lot of things could be toxic to a cell, or the cell wouldn't like their surface and wouldn't be able to grow on it.
Picky cells.
Cells are picky, and some are more picky than others.
But sculpting a scaffold out of the right material was only a start. To turn one into a living body part, an ear, for example, it must then be seeded with cells. A few weeks in an incubator allows those cells to multiply, covering the scaffold. Then comes a rather strange test. This is really creepy. I mean, mice are creepy enough, and this one has no hair and a human ear growing on its back.
Yes.
He doesn't seem to mind that he has an ear growing on his back.
No, he knows he's here for a bigger purpose. But this is a very, very important step in the science, because on the back of this animal, we're actually incubating and growing perfect cartilage in the shape of a human ear. And it's completely connected to the blood vessels, so that it's just like a native ear in a normal circumstance.
And the head of a person.
That's correct.
So when this finally gets implanted in a human, you don't expect rejection, as is so common with new body parts.
Exactly, because we're going to start with the patient's own cells. It'll make his own tissue, and therefore the body will accept it.
Within a year, Vacanti and Langer expect to be implanting their ears directly on the heads of soldiers wounded in Iraq and Afghanistan. But these will not be the first recipients of lab-grown body parts. Already, patients of other doctors have received blood vessels, skin, muscles, even bladders built the same way.
まあいいや。というふうに、まあこの BBC ドキュメンタリー1995 about more than a quarter century ago, but the very widely it is very astonished. Okay? And firstly, the skin is firstly used as a regenerative engineering, because from the single cell on this plate or shale, some tissue is easily to be made. So therefore, firstly, this kind of tissue engineering, as a skin, cultivating a skin is widely used. Firstly, okay, you may understand. From only the small amount of cell, this kind of skin is also cultivated easily, and it is used for some fire injured or some other injured tissue will be put into, and then by using his own patient's own cell, so therefore the no rejection to this new skin. So therefore it is widely used. It has already widely used here. And then the other part, for example, this is the tube for the lung. Tube for the lung part is also here, and some, for example, this is in the cat's case is maybe some nerve cells is also cultivated, and then the cell, the brain cell is inserted. For example, the aborted body's brain cell is injected into the elderly people's brain to prevent the Parkinson's disease or some other brain diseases. This is already practically used. And then the other case is this is the vessel, the generation, by inserting to the own cell inside of this, and then it is also working well. Spinal nerve damage. ちょっとこれ。Brain repair itself とか、まあいろんなのがありますけど、can action neuron replacement human brain cell とかなんかいろいろあります。まあいいや、skip. And then of course the liver. In this case, not only his own cell, but not only other human cell, but the pork's hepatic cell will be cultivated to make the liver module is also tried. This pig's cell is some artificial operation will be made to the pork cell, and then it is cultivated to replace this kind of the liver module to working in place of the human liver.
The field of regenerative medicine is moving from the realm of science fiction to science fact. From fingers and ears to complex organs like livers or hearts, scientists at Wake Forest University are making headway into growing human body parts. Let's take a look.
This is no ordinary printer. It's being configured to print living organs. Researchers have filled the ink cartridges with a cocktail of cells and nutrients. Today they've printed a rat heart. In the future they hope to print human ones. They watch as the newly made heart begins to beat. This novel process is called bioprinting.
Same thing with printing the organ. We have so many different types of cells that we need to use over and over again. Just put them in the right sequence.
Serious burn victims may soon benefit from the research.
Instead of waiting for the skin itself to provide this material, which takes around like 2 weeks, we are providing it right away. So forming the seed and providing the bedding for the cells so they can grow fast and immediately.
This ferret liver had all its own cells washed away, and the remaining tissue has been coated with human liver cells. After spending some time in a bioreactor, it will emerge as a human liver.
It's like they have their own eyes, or what we call receptors, that recognize the areas where they should attach or where they should be. And they do that on their own because we kind of mix them together and they sort themselves out.
これ今の話は バイオプリンティングってですね、3D プリンターで BioCell is printed not using the 3D scaffold. The 3D printer is used for the making some organization ね。っていう話と、あとセカンドリーがこのトランスジェニックオルガンっていうやつで、トランスジェニックは not only human cell but also other animal cell or other animals organ is used to injecting some gene inside of this the other animals organ ね。例えば for example the dog's liver, chimpanzee's kidney, the baboon's heart or pig's liver or some other, so like dog or chimpanzee, pig or mouse or something is used, some other animal's cell is used to as a source of the transgenic organ. それもちょっとだけなんかを見ると Should we grow the organ in a pig? とかいうやつを見てみます。
Hi, this is Kate from Minute Earth. In the United States alone, 22 people die every day waiting for a kidney, liver, heart, or lung transplant. There simply aren't enough donated human organs to go around, and we can't just go around stealing them out of random healthy people. But pigs' organs have roughly the same structure and proportions as human organs, and we already kill 500 million of the creatures every year for food. So why can't we just use their organs? Here's the thing. Our immune systems are really, really good at seeking out and destroying anything foreign to our bodies. So even human-to-human organ transplants sometimes get rejected. And pig organs are much foreigner. They have a super conspicuous sugar molecule on the surface of their cells that's basically a fight me sign for humans' organ-rejecting antibodies. But we've actually been able to engineer pigs whose organs don't carry those sugars. So, assuming we could take care of pig organs' other fight-me signs in similar ways, we might one day be able to transplant pig organs into humans. But there's a far more radical idea for pork-based organ farming. Grow customized human organs in pigs. Actually, it's not just an idea. It's an ongoing experiment in real life. First, we engineer a pig embryo that doesn't grow its own kidneys. Then we inject it with stem cells from the person needing a transplant. Then, as the modified pig embryo develops, those human cells grow inside the incubator into healthy kidneys made from the patient's own cells. At least, that's the plan. So far, we've only seen this experiment all the way through when the modified pig embryos were injected with stem cells from other pigs. We don't know whether it'll actually work with human kidneys, because we've halted all experiments with the pig-human embryos after just 4 weeks of development, because some of those human stem cells could develop into other human organs elsewhere in the pig's body, which raises a lot of ethical questions, like what to do with them. Even if the cells don't migrate, and these hybrid pigs end up producing lots of life-saving organs, what rights do we give to a part human pig, even if the part is just a kidney? What if it's 2 kidneys? 2 kidneys, a liver, and a set of lungs? In principle, we could use the same technology to grow human hearts, human spinal cords, and even human brains, all inside of a pig. And when we do, how will we know if that pig is still a pig?
まあいいや。ということで、なんか、in other animal, like pig, some, 例えばもう other, maybe you may be interested about in the pig is the source of the replaced organ for the human beings. まあ、this kind of technology is now developing. Okay? Right, that is the end of this talk. Sorry for the over